Hello, and welcome to the very first briefing in our series of briefings focused on TOSCA implementations. The title of our first briefing is Turandot, a lightweight open source orchestrator that enables TOSCA for Kubernetes. Our presenter today will be Tal Laurent. Tal is currently the principal software engineer at Red Hat in the CTO's office, specifically in the networking team. Before this, he worked at Cloudify on the ARIA TOSCA Orchestrator. He is also an active participant for a number of years in the TOSCA Technical Committee, and he will be helping us draft the TOSCA 2.0 specification. We will be having this series running until the early summer, and hopefully that will lead us into TOSCA 2.0. So we've got a lot of exciting briefings scheduled for the future. The first thing I would like to talk to you about quickly, we're going to run through this because we want to get to our presentations. We will be live streaming and recording this webinar. We will hold the questions until the end of the briefing. If we have time, we will review all the questions. If you post a question and we don't get to it, we will record it and get back to you. I will be following up with everybody and send them the link of the recording. And again, feel free to ask questions at the end or during. We will hold them until the end. And with that, I would like to hand it over to Tal.
Thanks, Dee. It's really nice to be here today. Let me share my screen. This is always complicated, isn't it? There we go. So today I will dive right into it, although maybe first I'll say thank you for the kind introduction, Dee, and I'm really excited about this series. Today I will focus, or we will be focusing on one specific product. Also mentioned January 27th, today is also International Holocaust Remembrance Day, and a reminder to all of us that working together with openness and diversity is an imperative. When we don't, bad things happen. Quick disclaimer slide. So I get asked this question a lot. Turandot is not on Red Hat's product map. It is a proof of concept of what is possible. The idea behind Turandot is really to further investment, collaboration, innovation in the Kubernetes and TOSCA spaces. That said, it absolutely does work. I actually just this morning did another point release of it, and I do encourage you to download it and try to play around with it. And hopefully this webinar today will help you get started. The documentation is still a work in progress. So, oops. Okay, this fun slide, I would normally ask you to close your eyes and imagine a perfect cloud world, but I want you to keep your eyes open so you can actually see the slides. And yes, I know that the unicorn here, I did notice this, that the shadow of the unicorn is wrong according to the sun. I know a lot of you engineers probably noticed this immediately, but in a perfect world, everything is possible. That's my thought here. So come with me on this journey of sunshine, rainbows, and unicorns to a world in which it's a parallel world to our own. It's an alternative Kubernetes universe. Now, let's go over where this timeline divergence happened, okay, in this perfect world that we're imagining. Looking a bit at the cloud native prehistory, this is, by prehistory, I mean pre-2014, so not that long ago. Many of us remember seeing the buildup towards Kubernetes. I'm listing only a few projects here. There were obviously more. I was working at the time at Orbitz, a company where we were working a lot with Mesos and Marathon as a way to manage our containers and applications in a cluster. Google internally was working on Borg. Later it open sourced it, and Omega was an extension that had to do with application workloads. Some of you might remember Makara. So OpenShift something that not everybody knows. Before Kubernetes, OpenShift predates Kubernetes, and at the time it really was not using Kubernetes, but rather a different management system. 2014 was the pivotal year. So for a while, the folk at Google were working on the next generation of Borg. Internally in Google, it was called Project 7. That was the code word. It was a reimagination of Borg using all the lessons they learned for a few years of deploying it. You'll notice too, Borg and Project 7 are both names coming from Star Trek. I'm kind of glad that they got rid of that theme and we've moved to the nautical names with Kubernetes. So yeah, Kubernetes was announced first in 2014, and it's the same year that Oasis released Tosca 1.0. Tosca 1.0 was an XML. This was the pre-YAML version. It would take 2 years of work to really release Tosca 1.0 simple profile and YAML. Yeah, 2015 is where our imagination here diverges. And what I'm imagining is that Kubernetes, when Kubernetes 1.0 finally gets released, it is actually based on Tosca. And yeah, this is our perfect world. What would have happened in this perfect world of unicorns and sunshine and rainbows? If Kubernetes had used Tosca, we would get a lot of great stuff. Just looking at this list makes me a little bit sad that we don't quite have it yet. But let's go over it because it is important. We would be able to declaratively validate all our resources. Now, Kubernetes, recent versions did get more support for data validation, data structure validation using OpenAPI v3. It is limited. Tosca, of course, can do, Tosca has much stronger data type validation. So it took some time. You kind of got it in Kubernetes. We could have gotten this from the start. We would be able to have extensible custom resources. So custom resources are an incredibly important part of Kubernetes. It really turns it into a platform and not just an orchestration environment. Every CRD in Kubernetes right now is a one-shot. Even versions of APIs, versioning in Kubernetes is really just a namespace addition. Every version of a CRD can be entirely different. Tosca, on the other hand, is an object-oriented language. So we would have gotten true type inheritance. So you would be able to take a CRD that somebody else created, extend it, and add your own data to it. And you would also have that relationship of subtype and supertype. Would have been nice to have this. We would have a formal topology graph with first-class relationships. Now, Kubernetes kind of has a graph already through the use of selectors, and they're very powerful, but they're also awkward. This is one of the first stumbling blocks, I think, of people learning Kubernetes is how to use these selectors and how to understand how a service connects to a deployment, connects to a pod. A formal topology graph, as opposed to just a topology graph, gives you a strong way to specify your design. And you actually get a really complete and complex database. You can derive it right now from the graph that exists in Kubernetes, but we would have a lot of advantages, I think, to managing large-scale applications if this was built in to Kubernetes. Tosca would also have given us properties and attributes. So this also evolved in Kubernetes. We now have the status in Kubernetes as a sub-resource. Tosca would have given this to us immediately through properties, which are unchangeable data points, and attributes, which are changeable data points. We would have integrated cross-referencing. So cross-referencing, again, kind of exists in Kubernetes to a very limited extent. So if you ever use the concept of ownership in Kubernetes, you know that Kubernetes can do garbage collection. So for example, if you delete a deployment in Kubernetes, you know that the replica sets and pods related to it would be deleted. And this is done through an ownership reference that is stored in. But that's kind of hard-coded in the system. And if you want to implement your own cross-referencing, you'll have to handle that lookup on your own. The Kubernetes API server will not manage that connection. TOSCA gives us a very rich way to interconnect parts of our topology using intrinsic functions. We would have a packaging system from the very start, so it would just be naturally there. We would also get interfaces and operations, a way to I'm calling this event handling integration. So these could be entry points into other orchestrators and subsystems that need to work with whatever there. Now, if you know, it's really hard right now in Kubernetes to actually talk to your services running in the cluster, especially if it's from the outside, right? So again, this is one of these stumbling blocks early on that are hard to learn about Kubernetes. How do I actually access my service? What is the IP address? How do I get it? How do I do that lookup? So there's internal DNS and other things, but actually calling APIs becomes kind of challenging. TOSCA gives us interfaces and operations as a way to define these entry points at design time. We would get service composition. This is a very powerful feature of TOSCA that allows it at runtime to substitute nodes for other nodes. And when we get to the demo, we'll see what does a node actually mean in TOSCA and how does that relate to Kubernetes resources. Last but not least, it would have put Kubernetes on the path to using an open standard with a common toolchain. So yes, I'm saying last but not least because that would have been a very powerful thing. Kubernetes as it exists right now has a bespoke system. A quick note, I don't want it to appear here that I'm saying that the group of folk at Google that were working on Kubernetes were somehow lacking vision or that they should have chosen TOSCA. It's really hard to fit it in my fantasy timeline here. And also another thing to think about, I don't think they were thinking of Kubernetes resources in terms of a language, right? If those who know a bit of the deeper plumbing of Kubernetes know that those YAML files that we use so much in Kubernetes, that is actually an indirect interface into the resources that are data structures written in Go and serialized actually to JSON or YAML. So the natural data structure in Kubernetes is actually those Go data structures. YAML became just a representation for it. TOSCA, of course, is something very different. It is a language that can be represented in YAML. So that kind of connection, my point is I'm not blaming anybody for not having done that, but I still wish this would have happened. It's not too late though. This fantasy is fulfilled, I think, in some ways by Turandot. Turandot really tries to make it as native as possible, so as close to this fantasy world as it can be. Obviously, Kubernetes does not natively speak TOSCA, so there are a few compromises here. However, I think you'll see in the demo that the experience is fairly smooth. So Turandot uses the Puccini TOSCA compiler, which does a lot of the heavy lifting here for actually processing the TOSCA. And it's interesting, if just in terms of lines of code, Puccini is, I think, 10 times bigger than Turandot. Turandot is very lightweight in a way. The core of Turandot is a Kubernetes operator running in the cloud that manages your resources and compiles them. There is a very useful, I think, CLI helper tool to do all the work. In terms of how we're modeling Kubernetes resources, so there's a one-to-one mapping. So if you're used to the YAML, the kind of raw YAML used in Kubernetes manifests, the TOSCA will look very, very similar. And of course, YAML is used on both sides, so it seems very natural. My point here is to say that it is not a high-level abstraction. It is absolutely a direct modeling of everything you have in Kubernetes. So there's no attempt to hide or add some sort of higher orchestration layer. This is Kubernetes. Another thing that Turandot does is repurpose container image registries for CSAR repositories. This is something Originally, when I worked on this was part of Turandot because I realized I needed a place to store these CSARs and the artifacts. Over time, I decided to actually turn this into a separate repository. So Reposure is another project right now, independent project for managing and connecting and repurposing a cloud-native registry. So I'm not going to go into it today, but yeah, it ends up being quite a lot of work dealing with authentication and authorization. So, oops. So it just works at this point. We're going to see TOSCA operations working directly on at the container level, or even KubeVirt virtual machines. One interesting aspect of how Turandot works is that there is an intermediary format called CLOUT, which is in between the TOSCA design time and the Kubernetes runtime. CLOUT is actually a fairly simple format. It is the output coming from the Pacini TOSCA compiler, but it is how Turandot really manages the entire workload as one service. In the end, it's really a summary of everything that exists in Kubernetes. So all the resources related to that specific topology, that specific workload. But it also includes stuff that is kind of hard to put into Kubernetes, things like policies, groups, concepts, logical concepts that exist in Tosca but don't have a direct equivalent in Kubernetes. Now, I could have created CRDs for all of these, but yes, that have gotten more complicated. So this is a lightweight format, and we'll take a look at it. I don't think it adds a lot of complexity, and I think it gives actually a lot of advantages in terms of seeing where things are right now. The Turandot operator makes sure to constantly update the CLOUT with changes to Kubernetes resources at runtime. Question that comes out a lot as well is, okay, well, how does this relate to Helm? Doesn't Helm already provide a lot of these features that that Turandot and maybe Tosca bring to the table here? The answer is no. I think Helm has Helm at its core is a text templating tool. You're working directly with a YAML manifest, and you're just generating YAML. Helm has a few other features, but I think it really falls short over everything that I've been presenting so far here. So that, the obvious, Turandot really introduces Tosca as a true language. Helm doesn't really have a language. It's a YAML generator. At Turandot, you can validate your entire design before you actually deploy it. Tosca is a very strictly typed language, and actually in Tosca 2.0, a lot of our discussions right now on how to get to the 2.0 release are about features that, how do we make sure that we can really have a fully validated topology and graph before we actually deploy it? Exciting discussions, and I hope some of you would be interested in joining and contributing to the work there. OASIS is an open standards body. Helm, it's a wing and a prayer. You really hope that your text templating will actually generate valid YAML and valid manifests for Kubernetes, right? Until you actually deploy it on a Kubernetes cluster, you won't know that it's actually valid. Tosca goes a long way to make sure that it is. Turandot uses, as I said before, the container image registry that already exists. So just to be clear, CSAR files are stored on a container image registry here. So they are not container images. You can't just run a pod based on them, but the database is already there, and there's a huge advantage in terms of building deployments of reusing something that's already there. With Helm, you're going to have to, Helm has its own chart repository format, and you're going to have to run that separately. So if you're really building a complex CI/CD pipeline internally with, many clusters, a huge cloud, lots of registries and repositories, Helm requires you to add another layer to that, a chart repository. So I do think that was a mistake in terms of architecture requirements there. Turandot does runtime policy-based composition. Here I'm referring to Tosca as a substitution mapping feature. Helm does let you do composition. There's a subchart feature, but it's design time. It's based on imports. It can't change things at runtime because Helm doesn't have a type system, right? Because Kubernetes doesn't have a type system per se. Turandot really lets you inherit types, so you can have a certain node type that is actually implemented entirely by another whole topology. A very, very powerful feature of TOSCA. Well, Turandot lets you create relationships between nodes that are first-class systems. So all these features simply don't exist in Helm. You can package container images in Turandot. I'll show you in the demo that, again, you can't do this at home. You will have to have that separate container image registry if you want to deploy Helm. So again, part of the problem, there's a lot of stuff that newcomers to Kubernetes find very difficult. They have to have a registry. If it's a public registry like Docker Hub, or if they have to deploy their own, Turandot makes it pretty easy, I think. You can also install arbitrary artifacts and containers with Turandot as well. So if you have a config file that you want to copy to that container pod, that's a feature in Tosca. Tosca features artifact management, and Turandot supports that. And you can run operations on containers. So again, all this stuff that simply doesn't exist in Helm. So am I being mean to Helm here? I don't think so. It's fair. Helm does some things, but does actually very little. I did put a little asterisk here. Turandot can package and deploy Helm charts. And if you do have a big investment in Helm, you don't have to throw it away if you want to upgrade to Tosca and Turandot. So you can still reuse that, and I'll even show that in the demo if I have time. So that's it so far. I'm going to jump to the demo immediately, and we can see how it all works. And the demo I will focus on a simple demo here, a hello world, because I want to showcase the basic features. There is a much more complicated demo, a telephony network service demo, which shows rich relationships, service composition, multi-cluster support, and using KubeVirt for virtual machines. We just won't have time to delve into it just because it is pretty massive, but it does exist in the Turandot GitHub repository, and maybe I'll be able to give a sneak peek of it at least. So without further ado, let's see what I have here. So I do have a Kubernetes cluster running, a fresh one that I just created. And let's start installing. So I hope the font here is big enough. And actually, let me remove how do I do this in Zoom? I will quickly stop my video and share again. All right, so you can't see my beautiful face anymore, but hopefully we'll be able to see more of the demo. So I just quickly set here the my current namespace to workspace just so I wouldn't have to keep repeating that. The Turandot command line tool is installed, and it does have a very elaborate help. There's no documentation quite online, but I think smart people will be able to understand how everything works. I'll start by installing the operator itself. And here, let's just make sure we're waiting for it to install. And here, I'll go to the workspace namespace. And you can see it first actually installed the reposure operator. The reposure operator makes sure to manage the registries. So, all right, there we go. So we have the two operators running. That was easy. And I do need to create with reposure my default registry. So reposure command line, let's create registry create. And let's create the default registry with Minikube provider here. Oh, oops, I think. Oh, when you do things live, you sometimes make mistakes. I'm going to do a quick uninstall here. Right. I forgot two things when I installed the operator. All right. My cheat sheet. So to install the operator, I actually want to give it a site name. And I do need to give it special cluster permissions because I'm reusing the internal registry within Minikube. And that does require access to authentication secrets that exist outside of my namespace. So, OK, this should work right now. And the reason I'm giving it a site name is for Turandot's multi-cluster feature. So every operator knows which named site it belongs to. So when a federation of clusters and operators happens, they know which workloads belong to who. So, OK, we should be good now. There we go. Everything's green. That's what I like to see. Let's take a look at, we're about to deploy a CSAR file. And actually, let's just deploy it first. It's Turandot service deploy. And we get the option here to deploy directly from a file. We can also deploy from a URL if we have them stored somewhere. And here we go. Oh, I do need to give a name to the deployment. Let's call it. Oh, dear. There we go. All right. Oh, let's give it a second to start up. OK, now it's up. So we have the service, and it is instantiating right now. And we can take a look at the cluster. And let's actually create another terminal here. And let's look at the OK, so we can see the logs. And from the operator, there's a lot going on. We can see it copying an artifact. So I'm going to show you soon that actually this CSAR file contains the container images and artifact too. So it registers on the registry. And OK, I think we should be up here. If we look the service list, yeah, everything is great now. It's instantiated, and it achieved its normal state. It's initialized, and we even have a URL here that if I open, I think I'll be able to access that container. Yes, here we go. Here's the hello world. And this is interesting. It says part of TOSCA node hello world. So part of the hello world is showing how I can actually run and configure that image after it's deployed. And I can see it here. Here's the hello world deployment, and it has a pod. And it worked. Let's look at how this service was designed. What's inside the CSAR file? So the CSAR file is just a zip. Those of you who are not too familiar with TOSCA. And sorry, the font here is a little small, but we're going to open the YAML file that exists at the root of this zip. And that is the service template itself. Now, the service template is written in TOSCA 1.3. The Puccini TOSCA compiler does track TOSCA 2.0 right now, but TOSCA 2.0 is still a work in progress. So I think Turandot, the decision was to use the latest release of TOSCA, which is 1.3. And it imports two profiles here. So it imports a Kubernetes profile and an orchestration profile. We're giving them namespace prefixes to access them more easily. And you'll see here that we start by defining a node type. And this, I kind of hinted it earlier on in the slides when I said, saying, well, what is a node exactly versus, say, a resource in Kubernetes? So my design decision here, I thought about this a lot. At early experiments, I really said, well, every Kubernetes resource should be a node in TOSCA. And I quickly found out that that might not be the best solution, because the whole, what TOSCA lets us do really is reimagine our workload and reimagine the topology in ways that make sense for us as workload designers. So the resources in Kubernetes end up being implementation details. What do I mean by this? If you think of an application, if we go back to our hello world, we have the hello world deployment, but for the hello world deployment to actually work, we also have to create a service for it. So here's the hello world web service, which opens the port. And those of you who are familiar with how Kubernetes works, you know that there's more to it than that. The deployment is actually a controller that creates a replica set. And that replica set is the owner of pods. So what we might consider a single node here is actually comprises 4, actually more than 4. Services also have endpoints, numerous resources in Kubernetes. They still exist. They're still modeled here, but we are able to think about it and conceptualize it as a single node. So where are all these resources? They appear as capabilities. So most of the Kubernetes profile that you import here is TOSCA capabilities. And I'll give you a quick show of it if I go back to, the CSAR file. So under profiles, we have the Kubernetes profile. And you'll see, so this is just the profile itself. So we have all these capabilities, lots of capability types. And this is when I said a one-to-one mapping to Kubernetes manifest, this is pretty much it. For now, I did this with this was hand done, a lot of copy and pasting from the Kubernetes documentation. So it's basically TOSCifying the Kubernetes API documentation. So everything that exists in the TOSCA in Kubernetes APIs has a TOSCA equivalent here. I do hope in the future to create a tool that will automatically create this TOSCA for me, because this was a lot of work. But it's also trivial work. It's just boilerplate copy and pasting. So for example, we have a service which is equivalent to, so the service capability type here is equivalent to the service resource in Kubernetes. But the very nice thing in TOSCA is that, of course, we have inheritance and object orientation. So for example, the load balancer inherits from the node. So we have node port, which inherits from cluster IP. Cluster IP inherits from service. And all we're doing is really changing the default type for that service, although load balancer does introduce extra properties and attributes. So we really see how nicely this actually maps between, I think, Kubernetes resources and the object-oriented world of TOSCA. So going back to this here, so we're creating an application node type, which is totally our own. And we're saying that it includes a deployment and a load balancer, which is a type of service, as we just saw. It inherits a few times, and services, it's a superclass. So when I say that all of these capabilities are here together in the node type, that's when I'm associating them into a single application. They're all going to be sharing this metadata. And so that metadata gets up being copied to all the different selectors, right? So we can make sure that the deployment, that the web load balancer service uses label selectors that will match whatever are there in the deployment. So for those of you who don't know Kubernetes too well, that might sound very, very cryptic, but yes, that's how one way Kubernetes is kind of weird in how it works here. But at least from the TOSCA perspective, it was pretty easy to do it here. I am also defining 2 interfaces on this node, and those are used to handle those configuration events or orchestration events that can happen after deployment. So this is, again, a very powerful TOSCA feature that is supported by Turandot. And I'm defining here, this is for demo purposes, 2 different interfaces. And the way I've modeled the interfaces here, that every interface type is a different kind of technology. And all these interface types have a single operation to them. Interfaces in TOSCA could actually have multiple operations. And it's just nice that the flexibility of Tosca gave me a way here to really model different kinds of technologies. So we have, one of them is a container command, one interface. And this container commands get executed by using the Kubernetes control plane. This is a very powerful feature that I think not enough people use. The Kubernetes control plane is, it runs through the Kubernetes API server. And what it does is allow you to use HTTP streaming. It's actually the SPDY protocol, not HTTP directly, but it can do HTTP style streaming of standard input and output and standard error to any container running in the system. So this is through an underlying Docker feature originally, although now with if you're using Cryo, it exists there as well. Point being that all of the containers and Kubernetes running have a built-in ability for you to interface with standard input and standard output, meaning you can run any command there and you can stream text input and output, or not just text, right? Any kind of data in and out to it. Very powerful feature that here is used for easily. Turandot does kind of the heavy lifting for you to make sure that you could actually run those commands. Our actual node template here uses that application type, and here's where we actually set values to the various properties. So I'm giving it a Kubernetes label, just a name for it. So this will be used for to connect really the deployment to the service. Here I'm actually creating the container as part of the deployment. So again, all these properties are really, if you've worked with Kubernetes before, it's exactly that. These are the Tosca versions of it, but as I said, it's a one-to-one equivalency between the Kubernetes keywords and the Tosca keywords. The big difference is Tosca is strictly typed. So all of this will be validated originally before you even deploy. So right here, when I deployed the service, I would get an error if this didn't include proper Tosca and everything was not validated. So that's very important, because before I even start deploying a complex design to the cloud, I can make sure that it is ready for that deployment. This is where it gets more interesting. So the image keyword in Kubernetes, you're supposed to give it an image reference, a Docker-style image reference. So Docker-style image references are kind of weird. This is part of the inheritance of the Docker background of Kubernetes, which is very unfortunate in many ways, and I'm glad we're slowly moving away from that. But one thing, it has to work with a Docker-style image registry, and it works by you give it kind of a host name / repository name / tag. It's not a URL, but it works kind of like a URL. It's just not a standard URL. But here you see, instead of giving it the actual value, I'm calling a Tosca function, a Tosca intrinsic function. And the Tosca intrinsic function is get artifact. This is a standard Tosca function. And what this get artifact call will do will actually, so I'm saying I want the artifact named image on self. So this is my own node template here. Let's look at the artifacts that are being attached here. So here's the artifact named image. It is of type container image. And the location of it, the file of it, is here as a tarball. And if I go back to the zip file for the archive, for the CSAR, so here it is, artifacts, images, and here's the tarball, hello world.tar.gz. So what happens here, this is very powerful. So I've actually included a tarball of the whole container image. And Turandot will know, because because this is of type container image, Turandot will extract this image from the CSAR, upload it to the container image registry. And once it's uploaded, we'll generate that container image reference pseudo URL, and that will be the return value here. So if I actually look, we can actually go back to the cluster and look at the deployment here. And we can go here. Let's look at how let's look at the YAML manifest here. So here we see the template metadata. Here's the spec. Here's the image. So this is what the get artifact function call returned. So it gave me an IP address, which is the internal Minikube registry in this case. But again, we have that repository operator that handles all the access to registries. So it could obviously be a very robust registry that you're running for your organization. If it's Quay or Harbor or any of those really production grade registry servers. And yeah, it gave me the kind of repository name and the tag name. So it did it all for me. That was pretty great. It means that I can have a really self-contained packaged application, right? My CSAR file has the container image and has the TOSCA and has everything you need to deploy it. So there's no additional steps, right? Once I have Turandot installed, I can just do service deploy with a CSAR and it's all there. What else do we have here? Some more Kubernetes stuff. I have, this is web. If you remember, the web capability is, if I go up here in the node type, it is of type load balancer, so it's a type of service. And here I'm giving it its properties. And I'll notice another quick plug for a shameless plug for something I'm working on. So, working with YAML, and you might think, oh, it's kind of hard to remember. I have to scroll up to remember what web is and what the properties are. I'm actually working on a language server for TOSCA, meaning that it could integrate into editors very easily. So you'll be able to have code completion. So if you do properties here and you'll start to write a property, PO, and it will automatically show you that ports is one of the properties and give you a quick description of the type of the data and everything. So I think that'll make it more pleasurable to write to TOSCA. In any case, the compiler will let you know if you made a mistake here. And so you can't make mistakes. TOSCA is very strict. There is an attribute here for the ingress IP, and I am initializing it with a value. That's just to make sure that here, before this value was added here, it would have shown that unknown. Here are the two interfaces. So this is, again, very interesting. One interface, so the first interface was of type container command. So as I said, this uses the Kubernetes control plane to execute commands. And it has these inputs, which are just arguments in the command line. And I wanted to run this command, which is a shell script. And the argument will be the node template name itself. So this $$ is a kind of a way to insert it. And in order to run this command, I want you to copy over this artifact. So the configure artifact is down here. So the configure artifact is an executable. It is this file. So if I look in the CSAR file, oops. If I look in the CSAR file, it would be, oh yeah, under artifact scripts and configure.sh. So this is a bash script. And you can see what this bash script does. So the hello world demo that I showed you is just a Node.js application displaying this page. But what I'm doing here is, so this bash script, what it does is, so this is the Node.js application. This is where it's installed. And what I'm doing is updating the web page. So sorry about the bash wizardry here, those who don't know. Here's the HTML. I'm just updating the bash, updating the web page, the HTML for it with this text, part of TOSCA node. And I'm using node template, which is simply the first argument sent to the bash script. That first argument is this, right? This the node template name. So that's what made sure that here, I got the node template name from TOSCA, hello world. And that node template name is up here. So I know this is not an exciting application. This is a demo to show how everything connects together. So again, very powerful, right? All I needed to do was include a bash script inside my CSAR file. By giving it the type executable, it makes sure that when it's copied over, the executable bit for the file will be set. So I would be able to actually execute it via the interface here. So this shell script will be able to run. And yeah, I think pretty powerful stuff. There's another type of interface here called a scriptlet. I will briefly mention what it is because I want to move forward and get us to a Q&A session as well before we end the presentation. What are these scriptlets? So this is an interesting feature in that CLOUT format. So I mentioned in the slides, you remember that CLOUT is the intermediary format between TOSCA and the Kubernetes resources. Let's take a look at it. So for that resource, there's a CLOUT command that I can actually extract the CLOUT for that specific service. What I got here was a huge YAML file with a lot of data. What's going on here? I'll show you another way to reach it. So if you go to the Puccini compiler website, you see a quick link here at the top to check out this live demo of Puccini Tosca running in a browser. If you click it, you'll get this mini Tosca ID. And the way it works is it's running entirely within the browser. There's no server-side code here. The Puccini Tosca compiler is written in Go, and you can actually compile it into WASM. So all of this is WASM WebAssembly running in your browser. Could be very useful for all kinds of integrations. So I'll just show you how it works. Here I'm loading a sample that's just built in of some Tosca, and then I can click parse and compile. And here I get the CLOUT output. So that's equivalent to what we were seeing here in the command line. This CLOUT is essentially a graph database. The documentation is here, and you can see it's really not a lot. There are vertices, there are edges, and you can translate this and copy this directly into a graph database like Neo4j if you want to do searches there. And it's very general purpose. So the way it works is that from Tosca, we compile things to edges. So some of our edges here would be node templates. Some of our edges would be Tosca policies. Some of our edges would be, some of our nodes would be Tosca policies or be groups, et cetera, et cetera. So this is a normalized representation of Tosca, but once it's compiled to CLOUT, it kind of lives on its own. And so day 2 changes that happen to our design will happen based on this CLOUT. And all of this is just to say that you'll see within CLOUT these function calls. CLOUT allows you to embed JavaScript scriptlets inside the CLOUT to do a lot of your operations. So Puccini comes with this kind of internal JavaScript runtime, which allows you to run these little scriptlets. What can you do with these JavaScript scriptlets? So let's look at the scriptlet that we're running here. Our scriptlet call. So the scriptlet is actually not an artifact. It is embedded into our Tosca using this metadata. So it's under scriptlets, set output. And here we go. So here's some JavaScript that you can do some internal stuff within CLOUT. So it creates this JavaScript environment that allows you to manipulate the CLOUT. So the reason you would do something like this is if you want to make changes to the topology. So for example, to scale out the service, you can update the CLOUT by adding nodes to it. And Turandot will make sure that this CLOUT will, as an intent, will then be deployed to Kubernetes. So there's a lot to say about what you can do with this here, but it has to do with the fact that there's an intermediary format between Kubernetes and your Tosca design. So I'll quickly just show that we also have another example, because I am running out of time, of we have the hello world. What is it called? Helm hello world. So I want to show you how we can integrate Helm. Oh, I made a mistake and deployed it with the same name. Let's call it Helm. Okay, here we have Helm. It's instantiating. And eventually we'll see it come up. Oh, I think I probably made a mess because by deploying it on the same name, I probably overwrote my earlier hello world. Or maybe not. Maybe it'll work okay. Oh, here we go. Hello world Helm did work. Okay. So let's look at the hello world Helm just to get a quick look at how it. Oops. Hello world Helm hello world. And let's look at that really. So the way Helm integration works is there's a Helm profile you can import into Tosca, and it is simply an artifact. So you can just zip your chart into Tarball, and then there's a node type called a Helm release. There are other node types for different ways you can use Helm charts. So this kind of is a one-to-one mapping of Helm features. And again, you can use the get artifact function. So Turandot will make sure to extract this chart from within the artifact. And then internally, it will run the Helm command line and basically do a deployment for you. So you don't have to have Helm installed locally, right? Helm is running on the operator, the Turandot operator in the cloud. So the integration is actually quite nice, right? You don't have to install Helm. You just have to install Turandot. And you have the added feature where you don't even need a chart repository, because you can store your repositories inside your CSARs. So it's better than Helm even, right? I don't know if I convince you of that, but I do want to show you that if you have investments in Helm, they're here too. I don't have time to go into the telephony example, but I will. But it is on the website, and I do encourage you to show you a quick link to it. It is a very complex multi-cluster deployment involving VNFs and CNFs, using KubeVirt, using Multis to create a separate data plane, and netconf configuration. And there's another project I'm working on called Candice, which is will be working with Turandot here to manage the netconf configuration task. So in other words, you would be able to have interface types, just like in our Hello World, that would be directly direct encapsulations of netconf network device configuration workloads. So again, I'm offloading that to a separate operator, and you solve one problem at a time. And with that, I am happy to stop sharing my screen. And Dee, will I turn it over to you to manage the Q&A?
Sure. Very nice, Tal. You've gotten a lot of positive feedback. I'm in awe. That's really cool. That's great the way it works. We are sort of closing in on the top of the hour, but I really wanted to ask, and there again, we will come back and answer these very specific questions that you folks have asked that we won't have time to get to. There is one overarching question that I think is super significant. If you can take a couple minutes and talk about it, and then I'm going to hand it over to Chris for a wrap up. But here's the question that I think is very powerful. Have there ever been serious discussions in the past 7 years to let Tosca play a substantial role in the Kubernetes ecosystem? If so, why is it not used more widely? And if not, why did that discussion not happen?
It's a good question, and it's really how I framed this whole presentation today, starting by that alternative timeline. I really wish, if TOSCA 1.0 was released a year earlier, it might have been just in time for that moment where engineers at Google were developing a Kubernetes. We've been working really hard towards building TOSCA 2.0 and thinking of it in terms of integration with the cloud native world. I think a lot of people early on had what's the word I'm looking for? Had the wrong impression of what TOSCA was for. TOSCA came with a simple profile which modeled what I like to call legacy clouds. It looked like something like OpenStack, but not exactly OpenStack. And a lot of people had the idea that TOSCA was a language for those kind of OpenStack type clouds. Not really. TOSCA always and ever was thinking of things more generally and semantically. And I don't know if it's a failure of imagination or a failure of PR or a failure of research, right? I'll put the onus also on people developing cloud platforms. Go out there and research and look at what standards exist and try to think how they could work with what's there. But, as I said, it's never too late. I think we're at a moment now where Kubernetes is grown up, used in production. TOSCA is moving towards 2.0. This might be the time where we finally get these worlds more integrated together. So thank you for that question.
That was great. Again, just the positive feedback. I hope you're seeing it. So we only have a few minutes left, and I think you're kind of leaving us with a call to action. And with that, I would like to hand it over to Chris Lowry. He is the chair of the OASIS TOSCA Technical Committee and the CEO of Ubicity Corporation. So Chris, if you could say a few things, that'd be fantastic. Thank you.
Yes, thanks Dee, and thanks Tal for a absolutely wonderful presentation. Just to put things into context, what we're trying to do with the TOSCA Implementation Series webinar is to highlight real-world implementations of TOSCA or real-world use cases of TOSCA to demonstrate sort of the richness of the ecosystem around TOSCA and the variety of applications for which TOSCA is being used. So hopefully Tal was able to convince you today that TOSCA is the perfect technology for cloud-native type applications such as Kubernetes and others. We hope to find other types of, or to demonstrate other types of scenarios where TOSCA is used in cloud-native environments. Our plan is to do these webinars on the last Wednesday of every month for at least the next 6 months or so. Our next one is scheduled on February Wednesday the 24th. The presentation will be done by Dr. Trivo from T-Systems in Germany. And what T-Systems will highlight is another very important aspect of TOSCA, which is portability and support for multiple clouds. T-Systems runs a platform called Open Telecom Cloud, which is one of the biggest clouds in Europe. And one of the key features of Open Telecom Cloud is the ability to move workloads between clouds for scale reasons, for reliability reasons, and what have you. And they have adopted TOSCA as a portable platform to support multiple clouds and to support moving workloads between clouds. So they will highlight that aspect of TOSCA and showcase a tool they have developed called Cloud Topology Designer, which is expressly designed to support portable workloads. So hopefully that will give you insight into one more important feature of TOSCA, which is portability and interoperability. And then we'll go from there into more applications of TOSCA as we get into March and April and so on. And as Dee suggested, what we'd like to do is by the middle of the summer, have this all culminate into a webinar announcing all the important new features of TOSCA version 2.0. So we are very happy you were all able to join today. We look forward to our next meeting, and hopefully you'll attend the next meeting and the ones after that as well. And again, thank you very much for joining today.